For a challenging question regarding vectors, our problem states the points A, 1, 2, 1, B, negative 3, 1, 4, and C, 5, negative 1, 2, and D, 5, 3, 7 are considered as vertices of a tetrahedron, being a three-faced equilateral pyramid as shown. Initially, we are required to deduce the position vectors A, B, and AC, where we are able to refer to the general rule AB equals B minus A, where B and A are considered as the coordinates of the individual vectors given. Hence, position vector AB could be subtracted through the given rule to result in negative 4, negative 1, and 3, whereas AC could be equivalent to 4, negative 3, 1. Next, by obtaining this information, we need to find the Cartesian equation of the plane that contains the face ABC. As a pause to these calculations, an overview of the Cartesian equation could be seen as per the following. Where the vector points x1, y1, z1, and directional vectors u1, u2, and u3 are arranged in the following manner. The equation is then deduced through the act of cross-multiplying these forms of fractions to result in the Cartesian equation of the plane. Hence, as an application of this concept, we could label the vector points of AB as x1, y1, and z1, where AC could be our directional vector to be labeled as u1, u2, and u3. Hence, we are able to formulate the general equation, which could be seen as the cross product of AB and AC is equal to x minus x1 divided by u1, y minus y1 divided by u2, and z minus z1 divided by u3. We are able to substitute our labeled integers as given. This could then be cross-multiplied as required into two sections, where x plus 4 divided by 4 could be multiplied by y plus 1 divided by negative 3, as well as z minus 3 divided by 1. These two diverse calculations result in two forms of equations, which could be seen as 4y plus 3x equals minus 16, as well as x minus 4z equals minus 16. We're able to set these equations to a product of 0 as a method to combine these two individual rules. Next, we can then situate integers and terms to diverse sides per the given representation. This would then require regular subtraction and addition operations to result in the overall rule 4y plus 2x plus 4z equals 0. As a method to simplify this equation, this could be divided by 2 to be seen in the form x plus 2y plus 2z equals 0. However, as a method to acquire an equation that corresponds with the plane ABC, we are required to substitute the given terms x, y, and z by points of this face, where we could utilize the vector of A, which is equal to 1, 2, 1. This is able to result in the integer 7 to create a Cartesian equation equivalent to x plus 2y plus 2z equals 7. Moving on to the final section of this problem, find the vector equation of the line that passes through the point D and is perpendicular to the plane. Evaluate the distance between these 2 points. Hence, to formulate an equation for this line, we are required to utilize the coordinate of point D, which is equal to 5, 3, 7, as well as a point that is perpendicular to this plane, where this could be equivalent to 1, 2, 2, as per the given Cartesian equation. This has been selected as it is referred to as the normal to the plane, being another term for the word perpendicular. This is also considered as the equation of the plane, ABC, to be required for this step. Therefore, we are able to formulate the equation 537 plus lambda, which could be defined as lots of, multiplied by the normal vector 1, 2, 2, which is then equal to 7. We are able to simplify this to create the vector 5 plus lambda, 3 plus 2 multiplied by lambda, and 7 plus 2 multiplied by lambda. As aforementioned, this coordinate could be equivalent to the terms x, y, and z. Thus, these diverse equations could be substituted in the following form. As a method to obtain the value of the term lambda, through substitution it could be simplified to 9 lambda, which is equal to negative 18, whereas lambda is made the subject, it is equal to minus 2. As the problem requires the distance from vector D to the plane, we're required to determine the magnitude of the vector of this particular line. Now we are able to substitute the value minus 2 with lambda in the given vector to create the position vector of the perpendicular point to the plane as 3, minus 1, 3. As we currently obtain the vector of point D and the vector of the perpendicular point to the plane, we are finally required to deduce the magnitude of its position vector, which is D to the perpendicular point, to be considered as the distance between these points, hence solving the question. Thus, through the subtraction of vector D, 537, by vector of the perpendicular point, 3 minus 1, 3, this is equal to 2, 4, 4. This could be substituted in the magnitude equation as a method to attain the distance between these 2 points, where terms x, y, and z is arranged in the form root x squared plus y squared plus z squared. This would result in root 36, which is a distance of 6. A high-level vectors question completed.